In this video, we're going to identify the properties of domain, range, and inverse for 9 parent functions. We'll begin by identifying the domain for linear. Domain has the letters in it. So consider that when writing your function box. What values go in to your function box? Well, x's are your independent variable. Those are the ones that go in as an independent variable. So we need to understand that this graph keeps going to the left forever, which is negative infinity. This graph goes to the right forever, which happens to be positive infinity, and all the values in between are also graphed. So we would connect from negative infinity to infinity. These are the values of x that work. This is why your domain happens to be all reals. Remember, if you write interval notation, parentheses are used when you cannot reach a value, and with infinity or negative infinity, you can never reach that. Range is all about heights, all about the values that come out, or y's. So if we look at our y-coordinates, we realize that this graph can go as low as negative infinity. This graph never stops getting higher. Okay, we might say that increases without bound. This goes to positive infinity. All the heights in between are connected. This is what makes up a range. So the domain and the range for a linear function happens to be all reals. As we move to the quadratic, understand that this graph does keep going farther and farther to the left and farther to the right, even if you don't necessarily see it immediately. Therefore, the domain happens to be all reals. On the other hand, the range is not all reals because there is a specific height that this graph does not go below. It does not go below 0. Now it includes 0, and we'll need to remember that, but it will keep increasing without bound to infinity. This is going to be our range. We can write it multiple ways. Since negatives are not included, but 0 is, we can call that the all non-negative reals. Or you can just simply say y is greater than or equal to 0. If you want to use interval notation, you will start at 0, go to infinity. But since 0 is included, we'll need a bracket. And again, with infinity, you use a parentheses. Cubic is similar to linear and quadratic because, in fact, all three of these are known as polynomials. So, because linear, quadratic, and cubic are polynomials, one very helpful property is to know that for all polynomials, the domain is all reals. So, cubic will be all reals. On the other hand, polynomials do not necessarily share the same range. In this particular case, we just have to recognize that our range is going from negative infinity to positive infinity and all the numbers in between. We're back to having a range of all reals. We'll now move on to the square root function. Notice that the domain starts at 0 and continues to the right to positive infinity. This again would mean that our domain would include all positives in 0, which would represent the non-negative reals. You can also say x is greater than or equal to 0 or 0 to infinity. If we look at the range, we'll also notice that it starts at a height of 0 and goes to positive infinity. And therefore, our range is just the same as the domain, all non-negative reals. When it comes to the cube root function, the graph goes from negative infinity to positive infinity. Therefore, the domain is all reals. Although it creeps up slowly, height-wise, it will reach all possible heights, and therefore the cube root will also be all reals. Finally, absolute values. The domain goes all the way to the left, all the way to the right. We'll say all reals. While the range starts at a height of 0 and works its way upward to positive infinity. Once again, the range will be all non-negative reals, y is greater than or equal to 0, or from 0 to infinity. We move to the last three parent functions. We'll look at f of x equals 1 over x, known as the hyperbola. Since we are dividing by x, we have to remember x cannot equal 0, must be excluded from our domain. If we look at the graph, here's the value of 0. The graph goes to the left to negative infinity. The graph goes to the right to positive infinity. But there is no point defined at x equals 0. And our domain needs to represent that. We need to show that it's going to be all reals except 0. We can also write that as simply x not equal to 0. Or you can say negative infinity goes to 0, then go 0 to infinity using the little union symbol to include both intervals, and the parentheses skips the value of 0. Well, because you're going to always go 1 divided by something, you will always have at least a positive or negative value. But again, you will not actually get at 0 a value of a height that's 0. And so this will also go from negative infinity to infinity, but not include 0. So our domain and range happen to be the same thing. All reals except 0. The only difference this time we have to say is y is not equal to 0. We move to inverse square. Once again, you cannot divide by 0, so we need to exclude 0 from the graph. Our domain will be all reals except 0. On the other hand, when we look at the range, because we are dividing by x squared, anything that's squared, both positive or negative, will eventually become positive. So 1 divided by a positive number will mean that all your values are going to be positive. That would be everything above 0. So we will need to say all positive reals. We're not going to say all non-negative reals because non-negative would include 0. We do not want to include 0. We want all the y's greater than 0. We've come to our last parent function. It's the greatest integer function. It has alternate names like floor function and rounding down function. In fact, the easiest way to remember the greatest integer function is to round down. So let's say we had a temperature of 60.5 degrees. If we were thinking of this as a thermometer, we would round down to 60 degrees. So what we would say is we round down 60.5, or we could write this as the int of 60.5, and we would come up with a value of 60. The domain can be any real number because you can round down any real number. But the numbers you get out will all be integers, and that will be represented simply by saying all integers. If you want to abbreviate the integer set, just say the letter z. Let's return back to our first 3 parent functions and find their inverses. If we have f of x, remember that's just function notation, a way of saying y equals x. To do an inverse, all the y's must become x, all the x's must become y. Now we need to solve for y to get our inverse, but we have. This is one of those cases where our parent function is its own inverse. F inverse of x equals x. If we're going to find the inverse for a quadratic, we'll need to again switch our y's to x's and switch our x's to y. But since our x was squared, so will our y be. It's y squared. But in order to actually solve for just y, or y to the first, we will need to square root both sides. In the process, we have to remember that the square root of y squared has to always be a positive value. Therefore, we need to make this what's called the principal root, which means we need an absolute value, and that leads us to having a possibility of y could equal both either positive or negative square root of x. And so when I write out its inverse, I might write f inverse of x equals plus or minus radical x. Remember, f inverse of x notation does not actually mean that this is going to be a function. F of x means it's a function. F inverse of x just means this is an inverse of a function. And this inverse is not a function because you can get multiple answers out because of the plus or minus. We move on to the cubic function. So as we go ahead and rewrite it, x equals y cubed. We need to understand that if we took a square root to a y squared in order to isolate the y, we're going to need what's called a cube root to both sides. And in the end, you do not have to worry about a plus or minus, and f inverse of x will equal the cube root of x. As we move forward with our inverses, there will be functions just like the cubic function in which certain skills will be introduced in future units. So, as we go y equals the square root of x, and we switch our letters out, and we go x equals the square root of y. In this particular case, to isolate the y, we will need to square both sides. What will end up happening is we will have f inverse of x equaling x squared. The difference is our domain needs to be restricted from 0 to infinity because those were the only values that were coming out before. If we're going to do the cube root function, and we have y equals the cube root of x, and then we rewrite it as x equals the cube root of y, well, we'll need to cube both sides. And we'll come up with f inverse of x equaling x cubed. We do not have the same restrictions because the cube root and the cubic functions, domains and ranges are all reals. When it comes to the absolute value, we do run into an issue. And I'm just going to leave it at this. If you switch the x and y's out, we'll just say x equals the absolute value of y. This leads to what's known as a piecewise function, but I don't want to get into that right now. So just leave it as is. As we move on to the hyperbola, and we have y equals 1 over x, and we have to find the inverse, we'll write x equals 1 over y. Now what I'm going to do is think of this as x over 1 equals 1 over y, and then I'll do a little cross multiplying, and I'll say xy equals 1. So if I solve for y, I'll divide both sides by x, and again, we have a situation where the parent function is its own inverse. If we do for the inverse squared, y equals 1 over x squared, and then we rewrite it as x equals 1 over y squared, we're going to need to cross multiply again. So we'll have xy squared equal to 1. We'll divide both sides by x, but realize we have a y squared, so we'll want to square root both sides, and eventually we'll come up with y equals plus or minus radical 1 over x, or if you want to really simplify it, plus or minus radical x over x. If you want to use the f inverse notation, go ahead. It seems I just left it out here. And for the greatest integer function, we're not even going to touch the inverse for that.